Okay, here we've got a context question. We kind of know it's going to be binomial because that's the topic we're on, but in an exam you'd have to figure that out. So what's going on? We've got 24 children being invited, but each one of them has only got a 0.7 chance of turning up. Seems quite low. I need it to be low for the question to work. But maybe there's some nasty case of flu going around, so they're not very likely to turn up. Okay. Anyhow, there are 24 children, and each one's got a given chance of turning up. So if I'm counting how many children turn up, then I'm counting the number of successors turning up in 24 trials. So this does look like it's going to be a binomial. Okay, with 24 trials and a probability of 0.7. So x must be the count of the number of children who do turn up. So x is the number turning up. Okay, what else have I got in the question? Well, she is not necessarily preparing 24 party bags. I need to know how many bags she does prepare. Okay, so still 24 guests. So this binomial is absolutely fine. But let's say B is the number of bags that she actually does bother to get ready. Okay, then she needs the probability to be less than 1% that she'll get caught out and won't have enough bags. So there's a probability involved, okay, which is to do with the number who turn up, which is x, and the number of bags that she's got, which is b. Okay, if x is b, then she's all right. There's a bag for everybody. If x is less than b, she's also all right. So the probability of x being less than or equal to b, okay, is got to be high enough. So less than 1%, that's the probability that she won't have enough bags. I want the probability that she does have enough bags to be at least 99%. In fact, I need it to be greater than 99%, so the probability that she runs out is less than 1%. So, all right, I've got my x set up, so I could now start trying out values of b. Okay, so if I thought that maybe 23 bags would be enough, I'd say 23 bags, okay, n is 24, p is 0.7. The probability of being less than or equal to 23 is this, which is more than 99%, so she would be okay. So I can simply repeat this again. This is trial and improvement. There's no quicker way to do this than trying out values, okay? Though I can speed up the process on my calculator, okay? Rather than just trying out, I could try out 22 next and so on. But what I can do is when I set up my binomial CD, we've always gone past this screen that gives us the option of either list or variable. I've always done variable up to now, but if I do a list, I now say, okay, I can try different values out. So values of the number of bags could be 23. We've already done that one. I could look at 22. I could look at 21. I could look at 20. And I could look at 19. And if I think I've gone far enough, I can say, okay. I just press equals again. It's remembered n is 24, p is 0.7. So now when I press equals, it has to have a bit of a think. It doesn't take too long. And it gives me all the probabilities here. So I can go straight to the ones I want. So I want the probability to be more than 0.99. But I want to see how far down I can go. Right, that one's 0.988. And that's 0.997. So therefore, those are the two relevant ones. So my values are 22 bags and 21 bags. So the probability of x being less than or equal to 22 equals, okay, if I highlight it, then I get the exact value here at the bottom, 0.9978. So that one's okay. But if I go down to my next value, the probability of x being less than or equal to 21 is 0.9881. Now that is less than 99%. So this is not okay. So therefore, the smallest number of bags that she can get away with this 1% probability, is 22 bags. Okay. So we're going to say make 22 bags, and that's our answer. Okay. All right. Then we've got to finally finish off by saying what assumptions were needed. So we read the question. We spotted it was a binomial situation. Okay. So using a binomial was sensible. Binomial assumptions. What are they? Well, p has to be fixed, but it tells me p is 0.7. Okay. So it must be the other one. Are the trials independent of each other? Okay, well that means, does one person not coming to the party make it any more or less likely that someone else doesn't? Well, actually, if they're suffering from flu, and that's the reason why there's a low probability, then they wouldn't be independent, because if one person's got flu, then they probably all know each other. Others might have flu as well. So the assumption is that the children's chances of not coming are independent. And I can state this simply like this. So it's probably, I have to hope it's nothing to do with flu. Maybe Sophie just isn't very popular. They don't like her much. Whatever. Anyhow, they need to be independent. That's the assumption.